here. I think we're back online now. Okay, couple of things very quickly. I hope everyone is working okay with Canvas. I mean, Canvas is behaving properly. I hope it is, because on my end, it's not doing a good job. I'm having challenges with respect to trying to access some of the previous assignments that I need grading, and it's not accepting some of the grades. Anyway, I got tech support on it. We'll get that straightened up. So yeah, there's a number of activities that I need to grade that have not been graded, and I will make sure those things get done by the end of the week. I don't know, I hope you got an email. I sent an updated syllabus. Again, I don't trust Canvas now. But I sent an updated syllabus just to make it all legal and all that. It basically changes the times and the due dates. And I stated in there that it's updated due to the extended spring break. So I hope you got that, So if not, let me know and I'll make sure you do get it. Excuse me. Now we're getting pretty good, close to the end of the semester, actually. So, keep on top of the assignments and look at your grades, see where you're going, what's happening. If you need help, please, I can't overemphasize it. Let's get some help. You need, we got tutoring. If you need to talk to me, I know I don't have office hours, but I don't have a problem with respect to taking some Zoom time in between my classes, Tuesday and Thursday, and we can meet maybe for a few minutes to get things straightened up. But if you need that, shoot me an email. We can pick a date, Tuesday or Thursday. It'd be between 2:30, 3:30. Be right after this class. If you're in this class, we can go start right after this class, or wait to 2:30. And then at least at 3:30, because I got to prep for the next one coming up. Okay, so anyway, let us continue with where we ended, and we ended on slide 28 of chapter 10. We should be done with this chapter. The next chapter, 11, is extremely short. It's roughly 11 slides, and we'll be done with that one real quick. And then 12 may take a little time. I did change the due date. I didn't realize that. Let me share that with you. I had the activity for chapter 10. Remember, I stated that I won't make an activity on a homework due until after we're done with the chapter. Obviously, we're not done with chapter 10. We'll be done with it today. So I moved it. It was due on Monday. So I moved it to Wednesday. Okay. All right. And remember that if we've not done with a chapter and you see that there's a homework that's due, ignore it. Send me an email. Say, hey, are you going to move the thing? I may have got past me and I forgot. So no, I won't make anything due until we're done with that particular chapter. All right. So going back to chapter 10, we ended up in slide number 28. We were talking here about reactors, chemical reactions, and this one is a double displacement reaction. Okay. Now, when you see this type of a problem, the first thing I hope you notice is that the reactants are soluble, and hence the AQ. They're soluble in solution. Okay. And the thing is that we're going to look at the products now. To determine whether a double displacement reaction occurs is we need the solubility rules. Okay, solubility rules. And in essence, what happens here, the cations and the anions just simply exchange partners. Now, since we have aqueous solutions here, my suggestion is to write everything in ionic form first with the ions, so that you can put them together properly with the correct number of cations and anions together. Okay? Don't assume that because there's two chlorides here, when I put silver and chloride together, now I'm going to end up with silver with two chlorides. Okay? You can't do that. So break everything down. And we know that, well, what's going to happen, let me change the color here. What's going to happen is we're going to change partners, right? So the barium is going to hook up with the nitrate, okay? And that'll be the new ones. And then the silver is going to then exchange partners and combine with the chlorides. So I'm going to write it in that form with respect to the ions, putting them together so I can put them together correctly. So we got barium. We know that barium is in group 2, and barium, the ion barium would have a barium +2 charge. Again, that's denoted by the 2 chlorides in barium chloride, because we know that the chlorides have a -1 charge, okay? Well, the nitrates, you can look it up if you forget, on the polyatomic ion table, the nitrates have a -1 charge, okay? Now, the other group is the silver, the other metal is silver, and we know that silver will always have a +1 charge, always. Remember those ions with the constant oxidation number that we talked about a few chapters back. The chlorides being in group 7, when they become ions, will have a -1 charge, okay? So those are the ions, the new ions that are going to come together, and I put them in ionic form first so we can put them together correctly with the right ratio of cations and anions. So the barium, you can see, is a +2. The nitrates are a -1, so that tells me I need 2 nitrates. So the formula for barium nitrate is, we will need a parentheses because we need 2 nitrates. Okay, that will be that formula. And then the silver chloride is a +1, the chloride, and the chloride's a -1, so it's a simple 1-to-1. Okay, so its formula will be simply AgCl. Okay, now we have the correct formulation of the products that will be created, okay? Now, before we go any further, let's find out if this reaction will proceed. And we do that by determining, looking at the products only. And the products that are insoluble would tell us that, yes, we have a reaction. If both products, that is, if both barium nitrate and silver chloride are soluble, as defined by the solubility rules, then we have no reaction. Okay, so let's determine whether we're going to have a reaction or not. Let me change the color here a little bit. And so we're going to look at barium nitrate first, okay? We know that the nitrates, number 3 here, are soluble regardless of what the cation is. And so barium nitrate then would be a soluble species. Yeah, that's an AQ. All right. Barium nitrate will be soluble because number 3 in the soluble column tells us that all nitrates are soluble. Good. Silver chloride. Well, we go to the halides. The halides here, number 4 in the soluble column, normally are soluble. Okay. However, when they are combined with the heavy metals, specifically silver, mercury, and lead, and the one we have here is silver, it tells us that it is insoluble. Therefore, it's a solid. We denote that by the physical state S, telling us it's insoluble. Therefore, this reaction proceeds as written, okay? Now, remember, even though it's insoluble, it's a weak electrolyte. There is some silver chloride in solution, but 95% of this silver chloride is in combined form in a precipitate. Now that we determined that it is a reaction proceeds, well, we got to balance it. Okay, so let me clean up my act here a little bit so you can see what's going on. And the thing about double replacement reactions, if you follow any polyatomic ions that are in the problem, then you follow those with respect to balancing them, everything else falls in place, okay? For example, we started off with 1 nitrate group, but we ended up with 2 as a product, right? So what if we put a 2 right here in front of silver nitrate? That would balance out the nitrates. Well, in the process of balancing the nitrates, we increase our silver by 2, right? No problem. Now we go back to the problem, to the products, and we put a 2 in front of silver chloride. That balances the silver, which then affects our chloride. So we go check, go back to reactants. We got 2 chlorides. No problem. Because by default, barium chloride already has 2 chlorides. So the chlorides are balanced, okay? Then the last item is barium. We got 1 barium on both sides, and lo and behold, we got a balanced chemical equation, okay? Now, let me clear my mess, and we'll bring forward the not so messy reaction. Okay, and so that is a reaction. If we got a positive reaction because silver chloride, as defined by the solubility rules, is insoluble in an aqueous solution. Therefore, a reaction proceeds, and then we balance it and we follow the polyatomic ions. Normally, 9 times out of 10, when you have a double displacement reaction, you generally have some polyatomic ions to work with here. All right, so that's a double displacement reaction. Now we have what's called redox reactions. This is not a new type of reaction. A redox reaction is that the term redox is short. It's a combined word that comes from reduction and oxidation, okay? Now, what that means is this. When an element undergoes oxidation, guess what? It loses electrons. And so, for example, if we had sodium metal, it undergoes what we call oxidation because it will lose an electron. This is oxidation. And so what do we know about metals? Metals, as we know, lose electrons. That is, they have the propensity to lose electrons. So metals tend to undergo oxidation in general. Now, when you have a single replacement reaction, remember we exchanging the metals. And what's happening there is one metal is gaining an electron and the other metal is losing electrons. And so we have what's called a reduction. When an element gains an electron, it undergoes reduction. So let's take the, let me clear that up here. Let's take the chlorine element, just itself, one atom of that. Well, we know that it's in group 7. It's a non-metal, so it has a tendency to gain an electron, okay? It gain an electron. So its electrons are on the product side of the arrow. We call that reduction. Okay, notice there's sodium that it lost an electron and it underwent oxidation. So the electron is in the product side of the arrow. Okay, so if we take these two words and combine them, we have what's called a redox reaction. Now, redox reactions is a general term for most of these types of reactions you talk about. A single replacement is a redox reaction. A combination reaction is a redox reaction. So is a decomposition reaction, okay? And some combustion reactions are also redox reactions. And that is in that process of reaction that one moiety will gain electrons and the other one will lose required electrons. Now, this happens simultaneously. It doesn't occur separately, okay? It is the yin and the yang of chemical reactions, if you will. They don't occur by themselves. If an element undergoes a reduction, its partners undergo oxidation, okay? As we speak, if you're running off a battery right now, you've got a redox reaction because on one side of the pole of the battery, it is picking up electrons, and the other side of the other pole, it is losing electrons, and it's occurring simultaneously. Okay. Now, when you plug that in back into the electrical outlet, you shove that reaction process back. You reverse it. So when you push everything uphill, so to speak, and then when you take it off the charger and you start using your battery, the process occurs simultaneously. These reactions are simultaneous. They just occur right away. Okay. So reduction is when the element's charge goes down because it gained an electron. And oxidation is when an element's charge goes up. Okay. Oh. As I stated, that they occur together. It's not one and by itself. Now, oxidation numbers, remember, are simply the same thing as the charge of that moiety, whatever that may be. We all know the elements have a natural state, have a charge of 0. Why? Because they have equal number of protons and equal number of electrons. Okay. It is only when you lose an electron or you gain electrons that now you change that oxidation number. You change the charge. You may lose 1 electron, 2 electrons, or 3 electrons, or even 4 electrons, and you may gain, those electrons in the other end. But what's happening is the oxidation changes. The oxidation number does change. Recall again, group 1A always has an oxidation number of a +1. Group 2A, oxidation number of +2. Group 3A, oxidation number of a +3. We know that group 4, it depends. Group 4 is like you're on the fence. You can either gain those 4 valence electrons or you can lose them. So your oxidation number can vary from a -4 all the way to a +4. Depends on the conditions. Now, once we pass that group 4, okay, group 4 is like tip on the fence. You can go one way or the other. If you're sitting on the fence, you can fall one direction or the other, depending on the reaction conditions. But before the fence, you're always going to have a plus charge. After the fence, always going to have a negative charge, okay? And that's why group 5 will often have a -3. Yes, it's a possibility they can have different, but Chem-130 always have a -3 charge because it picked up 3 electrons, okay? Group 6 picked up 2 electrons because remember, we're striving for the octet rule. And every time you lose an X number of electrons or gain an X number of electrons, you are becoming isoelectronic. Remember that term, isoelectronic. You have the same number of electrons as a noble gas, either in front of the element or the noble gas behind the element. It's a metal, okay? Because the noble gases are noble gases. They're inert. They have an octet. All right, group 7 needs 1, and obviously group 8 will always have an oxidation number of 0 because those are noble gases and they have fulfilled the octet with the exception of helium, which has a duet rule. Okay, so refresh your memory on this. We talked about this in previous chapters. Okay, so it's, we're using it again. I also gave you a list of elements that have a constant 100% time oxidation number. Group 1 always has, there's 6 elements in group 1. Always has a +1. Group 2, there's 6 elements in group 2. Always have a +2. Then we added aluminum. Okay, so that's 12, group 1 and group 2. Don't throw aluminum here, but I gotta add that. And so we have aluminum with a +3. We got the silver as shown here with a +1 always. Zinc +2. Cadmium +2. And then we had the 1A and the 2A elements. Okay, so we had 6 right here and 6 right here. That's 12, 13, 14, 15, 16. So there are a total of 16 metals that you know its oxidation state 100% of the time. That means that all the other metals that you encounter will have a variable charge, and it could be a 1 +1, a +2, +3. And those other metals, if you don't know what they are, you will always know what the anion charge will be. Okay, so you can calculate which metal of the variable charges you're working with. So refresh your memory on that aspect. So oxidation is losing electrons, and therefore our charge goes up. So we have copper here, for example, which has a 0 oxidation number, right? Because it's the element, it has a 0 oxidation value. And by losing electrons, what happens? Its oxidation goes up in the positive, our number goes up, okay? And so recall we got 0, and then we got positive in that direction, and we have negative in that direction. And so copper went from 0 to a +2. So its number, its oxide charge went up. So, all right. Yeah, stop one moment. I'll be right back, guys. Just give me about 3. Okay, I'm back. And so solid copper in this example is oxidized because the oxidation number went up. Whoa. Now let me clear my stuff here. Now reduction, went too many slides. Oh, I forgot something here. Because solid copper is oxidized, what is oxidized? What is oxidized is called the reducing agent. You may hear that term. Okay, in this case, copper underwent oxidation, underwent loss of electrons, and therefore is called the reducing agent. If you think about it, it makes sense because it is producing electrons. It is the agent that's producing electrons that something else is going to get reduced. Okay, makes sense? So what is oxidized is equal to what is called the oxidized reducing agent. It can be a little bit confusing, but give it some thought and you'll see that here, how it works. Gaining electrons is called reduction. Okay, so the charge goes down. Remember that scale I had there where sulfur here is in 0 oxidation number, and then by gaining 2 electrons, this number goes into the negative to a -2. Okay, so its charge goes down, if you will, to a -2. Now, so sulfur is reduced, and because it's reduced, it is called the oxidizing agent. All right, because it is the one that accepted the electrons that the reducing agent gave. So it is called the oxidizing agent. All right. As I stated, redox reactions, they happen simultaneously. You can't have one without the other. And what is oxidized and reduced are always the reactants. Here, we don't care about the products, whatever the products may be. The products are just the result of the redox reaction, okay? And so if one's asked, what is oxidized, what is reduced, we are talking about the reactant chemicals. And in whatever chemicals they are, if it's an element, you just mentioned the element, or the whole chemical, copper nitrate, for example. You would say copper nitrate was either oxidized or reduced. Depends on the condition here. Okay, so let's try an example here. Question is, what is oxidized? What is reduced? And what is the oxidizing agent? And what is the reducing agent? All right, so let's break it down. Think about this for a second, okay? Break it down. It's not that complicated if you give it some thought. Here we have copper +2. It has a +2 oxidation state. What happens after the process is we have copper. Look at its oxidation state. Okay, so from going from here to here, it went from a +2 to a 0. Now, think about this mathematically. If I have a +2 value and I want to get to 0, am I not adding to it 2 negatives? Yeah, those 2 negatives happen to be electrons, all right? So it's picking up +2 electrons here to go from a +2 to a 0. Good. Let's break down the other one. We have iron with the oxidation state of 0. It's the element. And its oxidation state goes up to a +2. Well, what must have happened? If it went from a 0 to a +2, its oxidation number went up. It underwent oxidation. So on top went reduction. This guy went oxidation. The copper underwent reduction because its +2 went to 0. So there's a reduction process. Okay, see how that occurred? Where am I? Oh. Now, if you think, well, why would this reaction proceed? Well, I direct you to the activity series, and you will find that iron is a lot more reactive than copper. And iron in the beginning is not in an anionic form as a reactant. And so this reaction will proceed because iron is a lot more reactive than copper. Okay, see how all these things are tied in? All right, well, let me clear up my mess here and we'll bring it in with this slide. Okay, and so copper goes from a +2 to a 0. So the charge went down, it got reduced. And to do that, it must pick up electrons, right? Think about it. From a +2 to a 0, I need 2 negative values, which are the electrons. All right. Iron went from a 0 to a +2 oxidation state. Its oxidation state went up. Therefore, it underwent oxidation. Okay. And so here, elemental iron was oxidized. The ion copper 2 was reduced. Therefore, copper 2 is the oxidizing agent, and the iron, elemental iron, is the reducing agent. Right? All right, here's actually there's a real life example. This compound is utilized quite a bit in, they do use it for cancer treatment. This cobalt compound, platinum. Anyway, you got cobalt nitrate, okay, CO cobalt nitrate. It looks like it's a +2 stage. Okay, well let's break it down before we bring in the others. Well, let's take a look at cobalt nitrate. Okay, we know that the nitrates are a -1 species polyatomic ion. There's 3 of them. That means that cobalt here must be a +3. Does that make sense? Yeah. All right. Over here, platinum is a 0. It's the elemental. All right. Now we go to the product side. Again, the nitrates are -1. Each one's -1. So this means that platinum must continue with the +2 state. And then cobalt became cobalt elemental. And so if we look from cobalt to cobalt product, we went from a +2 to a 0 state. If we look at platinum, so that means that it underwent reduction. Right? Cobalt nitrate underwent reduction because they went from a +3 state to a 0. Its oxidation number went down. Platinum goes from a 0 state to a +3 state. Its oxidation number value went up. So this guy must have underwent oxidation. It sure did. It lost 3 electrons. Okay, remember, loss of electrons is oxidation. Gain of electrons is reduction. Okay, once you're able to analyze everybody involved here, then you can determine what is oxidized, or answer what is oxidized, what is reduced. And so this is a rehash of what I just did with my pen. Cobalt went from a +3 to 0, and platinum went from a 0 to a +3 state. That means that oxidized is platinum, reduced is the whole compound, copper 3 nitrate, and also that happens to be the oxidizing agent, and platinum metal is the reducing agent. Okay, so what is the name? Cobalt. I'm gonna say copper. Cobalt 3 nitrate, Roman numeral 3. All right. So there's YouTube videos. You know, make sure you check them out concerning Dr. Kim's version of her predicting products, all these reactions we talked about. Okay. So summarize this whole chapter. Learn the solubility rules, or learn how to use them. You don't have to memorize them. Why? Because you got the periodic table there. Okay, so learn how to use it, and the activity series to predict reactions. Okay. Recognize and balance combination reactions. Okay. The 6 types of reactions we talked about. Decomposition reactions. Recognize and write products and balance single replacement reaction. That is using the activity series where you are replacing the metals. Okay. And double displacement, which deals with precipitation, which means you are using the let me write this down here. On the case of single replacement, you are utilizing the activity series, okay, to predict products. And the precipitation and double displacement, you're looking at solubility table, okay, to predict product. Thing to remember is that you're looking at the products only with respect to double replacement reaction. You're looking to see which of the products are insoluble, which tells you got a positive reaction. If both products are insoluble, and then there's no reaction. Okay. Acid-base reaction, we did a whole chapter on the acid of proton and hydroxide. Okay, that is the proton where we had the H plus. Okay, reacting with the hydroxide, which always gives us H2O or water. And then a combustion reaction. All right. Let me back up for a second. The combustion reaction over here, you always have oxygen to give you CO2 and a water, okay? And we're always reacting a hydrocarbon. So denoted by X and Y with respect to the subscripts, because these are species that are only made up of carbon and hydrogen. When we talked about methane, you got propane, butane. You're familiar with a lot of these. If you did any cooking this past weekend, you know, out there with a tank of gas, that is a propane, 3 carbons. Methane's another one. If you did it, you flicker Bic, that's butane, okay? 4 carbons. Okay. So identify what is oxidized, what is reduced, and who are the respective agents in any of these redox reactions. Okay, turn the table there. All right. So with that being said, congratulations, folks. Chapter 10 down, 5 to go. All right. Any questions here before let me back it up for a moment. Because the next chapter is like very quick. We got that 10, 11 slides. Any questions, comments? Okay, well, this brings us to chapter 11. And this chapter is entitled Thermodynamics. Now, what we are doing here, because obviously one of the requirements of the teaching this particular course for all the Maricopa systems is we have to talk about thermodynamics. But bear in mind that we are giving you like the tip of the tip of the tip of the iceberg of thermodynamics. There are people who that's their whole career dealing with thermodynamics. And if you break that word down, dynamics deals with the movement of things. Thermal obviously sounds like heat, energy. And so we're talking about heat and energy and how things move around. And we'll find that chemistry definitely has a lot to do with energy. It's very important. If you don't have the right amount of energy, you cannot get the right reaction to occur. It is required. There's a lot of variables with respect to a reaction. We tend to think that, you know, we stick A and B in a beaker and voila, magically, you know, we get product. It's a, you know, Harry Potter thing. Magically, this happens. But there's a lot of things that are going. They have to be just right. You got to have the right amount of energy. We got to have the right orientation with respect to these reactants coming together. They have to come together with the right amount of energy, the right amount of orientation, or nothing happens. You know, I kind of make an analogy with respect to playing pool. I don't know if anybody has ever shot pool. If you have or not, billiards is another name for it. But you know that, you know, you got the cue balls, and you know, if you want to make that ball in that corner pocket, you got to line things up just right, the right angle, right? If I'm shooting in the right corner pocket and I want to hit that ball and right at an angle, I got to hit it just right. I got to hit it with just the right amount of energy. Otherwise, I'm going to miss that pocket completely, or I may hit it too much. It's just going to jump out of the pocket, or it may not have enough energy to even go down the table to the pocket. Okay. And even especially if I want two balls to go in two different pockets, you got to time everything together. So this is very analogous to thermodynamics. We got to have everything set up properly, or else it's not going to happen. All right, so we call that the collision theory. Okay, everything is a collision, but it's got to come together just right and with the right amount of energy. For example, we have two reactants. They happen to be two diatomic molecules. They have two different colors you can see here, that when they combine, they will eventually, let me draw something here. Okay, when these two combine, it's not a good color. When these two reactants combine, we're going to end up with two new products. Notice they exchange. Now, what's happened here is this, is that we have to break this bond here between the two diatomic molecules, but then we got to create new bonds, okay, to give us these new bonds over here. You can see in the product. Well, for that to occur, we have to be just right. And this intermediate is an area where we are in the process of breaking the bond here and then creating the new bonds right here. Okay. We call that position, we call that a transition state, where we have, it's a hybrid. It's got properties of the reactants and properties of the products. It's like the metalloids, where they got properties of metals and nonmetals, okay? And so for all this to occur, we got to have the right amount of energy for it to occur. And not only that, the orientation, they have to line up just right. There are reactions that occur in your stomach, for example, to digest your food, that have to occur with the right amount of orientation. We have enzymes that do that, to put everything just right so we can break it down. Would those reactions proceed? Yeah, but it may take forever. You know, think about this for a second. All right, let's say you got two reactants in the room you're in right now, okay? Now, two tiny reactants you can barely see, and you release them in the room, just those two, you know, if I put those two together, I'm going to get a new product. You know that part. But if I only got one and one, my God, it may take forever in a room that for these two guys to come together with the right amount of energy, much less the right orientation to make the product. Now, I can increase the probability of that happening by maybe heating up your room, because now I get those molecules to move around, those two molecules to move around much quicker than normal, which increases the probability of them coming together to make a product. That's one way. Or I can add maybe 1 billion or 2 billion A's and B's together in my room. Now I have more population in here. Now my chances are increased to actually get those two to come together. So see, a lot of things occur. And that's why reactions never are 100%. Why? Because as you proceed, if I got 1 billion of reactants of A, billion reactants of B, yeah, eventually they're all going to react, but then my concentration drops, right? I get to the point where I got that one or two guys left that are so far apart from each other, they're never going to come together. I shouldn't say never. The probability of them coming together is pretty low, just simply because of concentration. All right, so this center part, excuse me, is called the transition state. Okay? Transition state. Now, there is an energy requirement here to get to the transition state. It's a very specific quantity. It's a measurable quantity too. We can actually measure that in the lab. We call that reaction kinetics. That was part of my undergraduate, graduate early years way back when, where we were looking at reactions and we can actually calculate the energy of activation for a process. All right, so we could increase the number of collisions for a reaction to proceed, okay? We just need more collisions. One way is to add more material, add more reactants. Now, there are limitations that you can do. That's going to happen where you may be limited due to the type of reactants you have, but you can add more reactants to increase the probability of these reactions to come together, reactants that come together. Or you can increase the amount of energy. That energy, the minimum amount of energy to get two products to come together is called the activation energy. That is a minimum. If you don't have it at the minimum, that amount of energy, you're not going to get a product. Think of it as a hill you got to climb. If you don't have the energy to climb that hill, you're not going to get up to that hill. You need an X amount of energy to get to the top of the hill. Okay? And that's denoted by what we call the activation energy. Now, we can do that by heating it. Yes, by heating your reactants, you increase the probability of the collisions, and also you put energy into the system to give it more energy so it can have enough to bypass or overcome the activation energy. Okay? And of course, the molecules have to be orientated. Now, we have no control over that. You know, most of the time, it's just a matter of chance that they come together with the right orientation. But later on, we're going to learn there are things out there that can help us. All right, so increase the concentration. Notice the brackets there. That's the concentration of reactants. We get more reactants equals more collisions. We're going to get more product. We increase the temperature. And we know that as we increase the temperature, the molecules move faster. We're going to get more collisions, more energy into the system. Okay, and that's increasing the rate of the reaction. Okay, we can add what's called a catalyst. And what that does is it kind of lowers the energy of activation for that process to occur. There's a lot of examples, and like I said, in your stomach, there's a lot of enzymes. We call those enzymes or catalysts that actually put the reactants and hold them together such that they're in the right orientation so reaction can proceed. Catalysts can be very hazardous. I had one example in my graduate days that blew up literally in my face. But I just happened to step away as I step away, the whole thing just blew up in the hood. And what was happening was running a reaction. There were trace amounts. We trying to figure out what went wrong. I forgot to do a rinse. I had to wash my glassware a specific way, and I forgot one step, which left residues of metal in the container I was using. And that residue of metal, specifically iron 3, caused the reaction I was doing to be catalyzed to occur much quicker, much faster. Normally, it took a few hours for this reaction to proceed. With that catalyst, and it went bam, it made a mess. So catalysts really help us out. Now, that energy of activation, that is the minimum amount of energy necessary or needed to react, to turn reactants to products. Okay. All right. Now we also have an equilibrium reaction. We saw a little bit of this when I showed the reaction of insoluble ionic compounds, where the bulk of it was still together. We showed a double arrow. Now, equilibrium reaction means that the forward reaction rate is equal to the backward reaction rate. Here you have an example of A plus B reacting in the forward conditions to give us C and D, and then vice versa. Okay. There's a lot of examples of this. One of them is the buffer. We talked about buffer solutions, specifically say the buffer in your blood. It's trying to maintain that pH. That's a good example of an equilibrium reaction. Okay. Now things can happen and you can shift the equilibrium one way or direction drastically, but in general, it keeps things equal, hence equilibrium. Okay. Now we can graphically demonstrate or show the transition state, the energy necessary, the energy of activation. And then we have something else called delta H. You see the little graph in the top right. That's the energy of the reaction. Okay. And then we got two positions here. We got where the reactants are at. They start off with X amount of energy, and then the products end up with X amount of energy. Well, let me do this. Let me first draw this graph. And so we have, okay, we're in red, so we have a graph here. And so we call this the y-axis is energy, arbitrary energy units for right now. So we can, load these up, arbitrary energy units, and just say, 10, 20, 30, 40, 50, 60, etc. So arbitrary energy units. And then over here in this direction, we have what we call the reaction coordinate. All that means is this, is we call this shorthand reaction coordinate. Okay, that means that if we got a reaction, and let's say we took a photo picture of a reaction proceed. Okay, at time equals 1 second, we take a snapshot and we measure the energy. We have a point. So we were to do that as the reaction proceeds, we end up with a lot of data points, and we can have a graph here of this particular reaction. Okay. And so when we do that, we know, let's say that the products, the reactants begin, both of them, with an X amount of reaction energy. Let's say 20, here's of the reactants. Right here, that's where they begin. And let's arbitrarily say they begin at 20 energy units, okay? Well, as the reaction proceeds, we have all these data points that we can collect, all right? And if we connect all the data points, we end up with that graph that we show in the top right corner. And then down here someplace, we have the products. After the reaction is done, the products themselves have an X amount of energy. And so we extrapolate over here, we can say, okay, we're just like 10 units of energy. We begin, and then at the end, after the reaction is done, and then reactants started at 20 energy units, okay? Now, if we take where the reactants began, we extrapolate, we come up to the center, making a dotted line like this. This point on top of the hill is called the TS, or the transition state. Remember that picture where we're getting bond breaking, formation, okay? That's what that is. And guess what? That transition state has itself an X amount of energy. So we extrapolate across, and that is 60 units of energy up there, okay? Yeah, guess what? We can take that difference between where it started and where it ended, okay? And so that's 60 minus it started at 20, that equals to 40 energy units. This example is this, in this example, that is the energy of activation. That means that for this crude example here, it requires 40 energy units to overcome that hill at the minimum. If I'm at 39, it's not going to hit that top of the hill, and it's not going to make product. Okay, so I got to have at the minimum 40 energy units. And so the reaction proceeds, and we go down the hill, and we ended up down here in products. Well, guess what? I can extrapolate over here all the way across to my graph, and that ends up with 10 energy units. Now, if I take the difference between where the products, delta H, is the product energy minus the reactants. In this example, the products ends up at 10 energy units minus where it started at 20 E. Guess what we got? Do we not have a negative value? Negative 20 E. Okay, delta H is the energy of the reaction. Okay, that's what's left over. And you know what it is? Because it's negative, okay, This is what we call exothermic. Remember that term we used before, exothermic, way back when? The energy here is negative, it's exothermic, it gives off heat. It is it's a hot reaction, it's warm, it gives off heat. Energy is one of the products, okay, for this reaction. Delta H is the amount of energy for that reactant. And it's simply the difference between the final energy of the products minus the initial energy of the reactants. And in this case, it happens to be a negative value, which tells us it is a exothermic reaction. Another way to look at it is that the final energy value level of the products is much lower than where the reactants were, which results in the negative value, okay? We can do the same thing for the next example where the thing is inverse. Instead of being below the energy, you know what? We can have examples where the product ends up right here, where the energy of the products is much higher than the energy of the reactants at the starting, okay, and this higher level, which we end, if we do the math in this in simple calculation, we end up with a positive value. And we call that endothermic. That reaction gets cold, okay, it requires energy from the system. All right, so that's how we come up with this particular graph. Let me clear my mess up here. All right, to explain these numbers. So the transition state, that's the area where we're getting bond breakage and bond formation, okay? Very unstable area. It's eventually going to fall over to products if I have enough energy to occur to get me into the product side. Now, delta H, that's the change of heat energy. That's the energy of the reaction. And that's simply the energy of the products minus the energy of reactants, as I demonstrated in my example there. Okay. If it's an endothermic reaction, okay, meaning that the delta H would be a positive value, energy is required for this overall reaction. So it takes energy from the environment and it essentially gets cold. It's a cold. I gave an example of the ice packs and the hot packs you can buy at the pharmacy. You buy them, smack them, the reactants get together, okay? It gives off heat, it gets warm, so you got a hot pack. All right, so you put it on your sore muscle, whatever you're gonna put it on. And the other one is the cold pack. You smack it off, so it gets cold because it's an endothermic process that's occurring inside that package. And then you use that coldness to put it again in your muscle, whatever's hurting. Okay, so that's what we mean by endothermic and exothermic. It needs heat from the environment, so it absorbs it from the environment and makes the area cold. And it gives off heat, gets hot. Okay. And so for an endothermic, heat or energy is a reactant. For exothermic, heat or energy is a product, okay? Sometimes here in this example, we give heat is what's being given off because we're talking about thermodynamics, but you can give off light. Light is a product, but we won't go into that part. So with that being said, if we look at this graph here, the question is delta H, is it positive or negative? All right, well, if you forget, well, do your simple math and just throw some arbitrary values here. We go 10, 20, 30, you know, just to see it graphically. So you can see that if I extrapolate here, that this begins at 30 energy units, okay, arbitrary units, I'm just calling them 30. Now, if we look at the final products and we extrapolate all the way across to where the products ended, we're at 10E, okay? So you can see that number-wise visually. And if you recall the delta H, the heat of this reaction was products minus reactants, P minus R. We can say that it's 10E minus 30E, which gives us minus 20E, a negative value, okay? So therefore we can answer this question if you don't see it. If you don't see that the products, their final energy is much lower than where the reactants began. You can look at it that way, and that tells you that this thing is a negative value and therefore exothermic. Okay, so be able to draw the energy profile for either endothermic or exothermic. In this case here, notice they're all the same, okay? We got 1, 2, 3, 4, 5 labels. Reactants, products, transition state, energy of activation, and delta H. Well, for exothermic, pretty straightforward, right? I hope you see products energy levels much lower than the reactants. While endothermic is vice versa, okay? And same labels, but a different, the energy of activation, same spot. That's that energy difference between the reactants and the, I'm having a hard time with my dotted lines here. Okay, and so here is my energy difference. Here's my transition state there. Here's my reactants. Here's my products energy level, so it'll be over here. But notice the difference, delta H. And then let's say if this was 10, this was 20, this is 30. So my products end up at 30. My reactants start off at 10. And so remember, delta H is equal to P minus R, which is equal to 30 minus 10, E, which is obviously 20 E units, okay? Positive value, okay? So that means I have a endothermic process. If I need my energy of activation, we could, let's arbitrary sakes, that's 60. My energy of activation would be 60 minus 10. So this distance here would be 50 energy units. That's how much my delta, excuse me, my energy of activation is required, necessary for this particular example. Right? So this is an endothermic process with respect to the drawing, the energy profile. Right? And then in this case, as I explained mathematically, we would have a positive value with respect to delta H. Okay. So these are the two energy profiles for exothermic and endothermic. And so the top one is exothermic, and the bottom one is endothermic. Okay. They all have the same 5 labels, so be able to label the reactants position, products, transition state, energy of activation, and delta H for the reactions, okay? Now, with respect to a catalyst and how a catalyst does or what it does, in the process of what it does physically, like I said, it probably can hold the reactants together, or put them in a position where they increase the probability of coming together to the right orientation and so forth. So in essence, what they're doing is they are lowering the energy of activation for this process to occur, okay? And so you can see here that if we compare the energy of activation, that would be the normal energy of activation right here. But with the catalyst, you can see that value is much smaller compared to without the catalyst. And so that reaction doesn't require that much energy to proceed and occur. There's a lot of catalysts. Catalytic converter in your vehicle platinum, I believe, or palladium. I forget which rare metal it's on, but that is a catalyst that allows for destroying a lot of the emissions coming out of your vehicle. Very expensive catalyst, by the way, and so that's why people are stealing them, getting the metal out of it. All right. With that being said, congratulations, folks. You are down to chapter 11. And so we got, after this, we got, what, 4 more chapters, okay? These will be a little bit longer, but I think we're going to be okay. We're going to have plenty of review time toward the end of the semester to help and review, because we're going to just keep going with our chapters until we basically knock them out. So we'll probably end up with 1 or 2, quote, study days, meaning there's no lecture, but I'll be here. You can come in with questions and so forth. Okay. All right.